Hello, everyone. Today, we will be discussing protection mechanism, self, detect and activate heater, detect and dump. The protection mechanisms of superconducting magnets can be categorized into internal and external mechanisms. The goal of the protection mechanism is to prevent the energy within the magnet from being concentrated locally when a quench occurs. The specific types of protection mechanisms are divided into passive and active categories. Normal zone propagation and flux conservation fall under passive protection, while detect and active heater and detect and dump are considered active protection. I will discuss the important points in protection and the challenges in HTS magnet protection. As mentioned earlier, the problem when a quench occurs is the concentration of energy within the magnet. If the energy is concentrated, it can lead to four major issues: overheating, overstrain, overpressure, and breakdown, which significantly affect the magnet. Therefore, the solutions include quickly removing the energy outside the magnet or dissipating the energy uniformly throughout the magnet. The classification of protection mechanisms is shown in the table below. Protection can be divided into passive and active protection. Passive protection includes the protection resistor, while active protection includes detect and dump, and detect and activate heater. Additionally, high-temperature superconductor, HTS, magnets have a stability margin that is about 100 times larger and a normal zone propagation, NZP, that is about 1,000 times slower. Due to these characteristics, detect and activate heater is difficult, and slow detection makes the use of a protection resistor impossible. You can refer to sections 5.1.1 to 5.1.4 for stability margin, and for normal zone propagation, NZP, please refer to section 5.2.1. In conclusion, the most important point in protection is to either quickly remove the energy or ensure uniform energy dissipation. Now, I will explain the various protection mechanisms. First, I will talk about passive protection. Passive protection allows the magnet to be self-protecting without relying on external intervention. Because all the stored energy within the magnet needs to be dissipated, a fast normal zone propagation velocity is essential for passive protection. The first concept I will explain is the size limit. The time it takes for heat to escape from the innermost turn of the magnet to the outermost part must be shorter than the time it takes for the current to decay as the energy in the magnet dissipates. The visible formula represents this principle and allows us to calculate the size limit that the magnet should have. The second concept is flux conservation. Let's assume the circuit is configured as shown on the right. As you can see in the middle, a 0.5 ohm resistor is connected in parallel. If a quench occurs in coil 1, which has inductance L1, the current in coil 1 will decrease. To conserve flux, the current in coil 2 will increase. As the current in coil 2 increases, coil 2 will also quench. This leads to an increase in the current in coil 1 again. Ultimately, the sum of V1 and V2 is determined to be 10 volts, and the currents in coil 1 and coil 2 gradually decrease. Through this process, the magnet is protected. Next, I will discuss active protection, specifically the detect and activate heater method. I will explain it using an animation. The circuit shown below corresponds to the protection mechanism, and the main coil depicted in the middle is illustrated in the right image. First, when a quench occurs in the central magnet, it is detected. Next, the external protection heater is triggered to apply heat to the areas that have not quenched. Due to this protection heater, parts of the magnet winding transition to the normal state. Consequently, The energy stored within the magnet is dissipated and eliminated in the initial hotspot and the normal zone created by the protection heater. Lastly, I will discuss active protection, specifically the detect and dump method. The circuit is shown in the diagram below. As indicated by the blue path, the magnet operates normally. First, when a quench occurs in the magnet, it is detected. Next, the switch connected to the power supply is opened, disconnecting the circuit. The current is then redirected through the resistor connected in parallel, driving the system into a persistent magnet mode. Thus, most of the energy stored within the magnet is dissipated in the dump resistor. Through this process, the magnet is protected. To summarize, the protection mechanism in superconducting magnets is designed to safeguard the magnet when a quench occurs. There are two main strategies involved. 1. Uniformly dissipating the energy within the magnet, and 2. Extracting the energy to the outside of the magnet. When a quench occurs in a superconducting magnet, it is crucial to dissipate the generated heat as uniformly and quickly as possible. In the case of HTS, high-temperature superconductor magnets, the larger stability margin means they are more stable. However, due to the slow normal zone propagation velocity, NZPV, HTS magnets are relatively more challenging to protect compared to LTS, low-temperature superconductor magnets. HTS magnets use active methods because of their slow NZPV. In contrast, LTS magnets, with their faster NZPV, typically employ passive methods. That concludes the presentation on protection mechanism, self, detect and activate heater, detect and dump. Thank you for watching.